Intro to sequences. A sequence is an ordered list of numbers. So these are some examples of some sequences. All of these are just lists of numbers, and each one is following some kind of pattern. Over the course of these few videos, we'll talk about all of these sequences. Sequences are infinite. For the purpose of the test, every sequence follows some relatively easy pattern. Now, in real mathematics, of course, there are incredibly hard sequences, incredibly tricky sequences. You're not going to have to deal with that on the test. Everything on the test will follow a nice, easy pattern. Sometimes it will be the job of the test taker to discern the pattern. More often, the question will present the pattern in some form and ask something else about the sequence, the value of a later term or the sum or difference of two terms, something along those lines. Let's talk about the notation for sequences. We represent the sequence as a whole by an individual letter, usually a lowercase letter, and the individual number in the sequence, the order in the list, by a numerical subscript. So for example, if I say a sub 5 equals 28, that means for some sequence, the fifth term, the fifth number on the list, equals 28. So 5 is the position on the list. I go down to the fifth number on the list, and the fifth number on the list is 28. We can also use the subscript notation to denote a general term of the sequence, s sub n. Here n stands for any natural number, so n could be 1, 2, 3, 4, etc. One way to specify an entire sequence all at once would be to give an algebraic formula for s sub n. For example, the equation r sub n equals n times n plus 2 defines a complete infinite sequence. For any natural number, we can plug in that number and get a number on the list. And so this gives us an infinite list. We could find, say, the third number on the list simply by plugging in n equals 3, plugging that into the formula. This subscript variable is also known as the index, which is a way to say the place on the list. So n is the index. Let's think more about this sequence. R sub n equals n times n plus 2. For practice, let's find the first few terms. So when n equals 1, we get 1 times 3, which is 3. That's the first number on the list. When n equals 2, we get 2 times 4, that's 8, the second number on the list. For n equals 3, we get 3 plus 5, that's 15, the third number on the list. For n equals 4, we get 4 times 6, that's 24. For n equals 5, we get 5 times 7, 35. And so the sequence begins with those numbers. Those are the first 5 numbers on the list, 3, 8, 15, 24, 35. Now, it would be very hard if you were given that sequence to discern the pattern. The test is not going to expect you to do that. But they might give you the formula and ask you to find things. Find any of these numbers, for example. Notice that if a formula is given, it makes it very easy to jump ahead to any term we want. So for example, the test could give us that formula and ask us for the 48th term on the list. And of course, we could just jump right there just by plugging in n equals 48. We get 48 times 50, then use the doubling and halving trick. So half of 48 is 24. We get 24 times 100, so that's 2400. That's the 48th number on the list. Here's a practice question. Pause the video and then we'll talk about this. So the test likes these algebraic sequences that are defined in terms of fractions of some kind. So here we get an algebraically defined sequence. We want to find the difference of two terms. So first we have to plug in n equals 10 and n equals 6. For n equals 10, we get a sub 10 equals 1/12. For n equals 6, we get a sub 6 equals 1/8. And now we're going to subtract these two. 1/12 minus 1/8. This is 2/24 minus 3/24. We actually get a negative number, negative 1/24. And that's the answer. Some basic patterns of which to be aware. A sub n equals n, that's just the sequence of all positive integers. So just the counting numbers, 1, 2, 3, 4, 5, 6, etc. That is the simplest of all possible sequences. A sub n equals 2n minus 1 is the sequence of all positive odd numbers. So very interesting. And if we just had a sub n equals 2n, that would be the sequence of all positive even numbers. A sub n equals 7n is the sequence of all positive multiples of 7. And similarly, if we had any factor times n, it would be all the multiples of that particular factor. A sub n equals n squared is the sequence of all positive perfect squares. A sub n equals 3 to the n is the sequence of all the powers of 3. These are very simple patterns, but may be used as building blocks in more complicated sequences. So here's a practice problem. Pause the video and then we'll talk about this. Okay, which of the following could be true of at least some of the terms on the sequence defined by that algebraic formula? So could they be divisible by 2, divisible by 3, divisible by 5? Well, first of all, let's just notice if we plug in n equals 1, the simplest thing, the first number on the list, what we get is 5. So certainly it's possible for some of the numbers to be divisible by 5. So that is possible. 3 is possible. Now if we plug in n equals 2, then we get 21, which is divisible by 3. So it is possible that some of the numbers on the list are divisible by 3. Okay, so far so good. So 2 and 3 are possible. Now we get to 1. Now notice, think about this. 2n, if n is an integer, then 2n has to be an even integer. 2n minus 1 has to be odd, and 2n plus 3 has to be odd. So b sub n is a product of odd times odd. So every number in this sequence is an odd number. So none of them are divisible by 2. So it turns out it is not possible for any number on that list to be divisible by 2 because they're all odd numbers. So 1 is not possible, 2 and 3 are possible, and that gives us an answer of D. In summary, a sequence is an ordered list of numbers. In the notation a sub n, n is the index, that is, the place on the list. An entire infinite sequence can be specified simply by giving an algebraic formula for a sub n in terms of n. Arithmetic sequences. One special kind of sequence is called an arithmetic sequence. An arithmetic sequence is one in which we add the same constant to get from each term to the next. So if you look at this sequence, you'll notice that to get from each term to the next, we're simply adding 7. That's how we go from one term to the next. So we could continue this pattern forever, just continually adding 7 to get the next number. Notice first of all, a really big idea. Any evenly spaced list is an arithmetic sequence. So this is powerful. One special case is consecutive multiples of an integer p. We would add p to get from each term to the next. Consecutive odd numbers, consecutive even numbers, or consecutive integers are also special cases of arithmetic sequences. Here's an arithmetic sequence. It would be helpful to find a formula for the nth term, so that, for example, we could find the value of a much higher term on the sequence. The test likes to ask about this. Remember, for the algebraically defined sequences that we saw in the previous video, it's very easy. If the test said find the 80th term in this sequence, all we'd have to do is plug in. Well, we'd like a formula that would allow us to do that for arithmetic sequences. I'm going to analyze the individual terms in the following way to look for a pattern. So I'll focus on this particular sequence, the sequence that starts with 5, and then we add 7 each time. So the first term is 5. The second term is 12. I'm going to write that as 5 plus 7. We've added 7 once. To get the third term, we add 7 again. So I'm going to write that as 5 plus 7 plus 7. Then the fourth term, we add 7 again, then add 7 again. And so what we have here, this stream of 7s. We have 5 plus a number of 7s. Notice that the number of 7s in each row, the number of 7s that we're adding, is 1 less than the index number. It's 1 less than the number on the list. In each term, the number 7 is added as 1 less than the index number of the term. This is a big idea. Thus, the nth term, a sub n, would be the starting term plus n minus 1 individual 7s. Of course, a compact way to add n minus 1 individual 7s would simply be to multiply 7 times n minus 1. So that means that the nth term of this sequence would be 5 plus 7 times n minus 1. Now we can generalize a bit. First of all, the starting term in general is a sub 1. We're familiar with that from the last video. The fixed amount we add each time to get each term is called the common difference, because if we subtract any two adjacent terms, we get this same number. We symbolize the common difference with the letter D. The nth term of an arithmetic sequence with an initial term a sub 1 and a common difference D is a sub n equals a sub 1 plus n minus 1 times d. That is a very powerful formula. Please do not simply memorize it. Please understand the argument that led to this formula so that you understand it more deeply. But we'll be using this formula quite a bit. Notice that one context in which evenly spaced integers arise is the set of all positive integers that, when divided by one number, give a fixed remainder. For example, this sequence, the sequence that we've been looking at, is the set of all positive integers that, when divided by 7, have a remainder of 5. That's what all those numbers have in common. When we divide by 7, we have a remainder of 5. Notice that the remainder is the first term, a sub 1, and the divisor is the common difference. That will be valuable, so hold on to that thought. Here's a practice problem, very simple practice problem. We have an arithmetic sequence. Find the 41st term of this sequence. Pause the video and work on this. Okay, well, the first term is 14. And obviously, we're adding 9 each time. That's how we're advancing. So the common difference is 9. So we can just plug into the formula. This is the general formula. If we want the 41st term, we plug in n equals 41. So we get 14 plus 9 times 40. 9 times 40, of course, is 360. Add 14, we get 374. 374 is the 41st term on this sequence, the 41st term on the list. Here's another practice problem. Pause the video and then we'll talk about this. Let S be the set of all positive integers that, when divided by 8, have a remainder of 5. What is the 76th number in this set? Well, remember that we said that the remainder, 5, that's going to be the first term on the list, because of course the lowest number in this whole set is going to be 5 itself. If we divide 5 by 8, we get a quotient of 0 and a remainder of 5. And then 8 will be the common difference, because we'll be adding 8 each time to get the new numbers. So we have our starting term, we have our common difference. That's our general formula. We plug in n equals 76 for the 76th number. We get 5 plus 8 times 75. For that 8 times 75, we'll just do doubling and halving. So it's 4 times 150. 4 times 150 is clearly 600, plus 5 is 605. And that is the 76th number on the list. Here's another practice problem. This one's a little bit different. Pause the video and then we'll talk about this. Okay, here it turns out that the first term is not known, the common difference is not known. We're just given 2 random terms somewhere on the list and we want to find another term. Well, think about it this way. Let the initial term equal b and let the common difference equal d. Well, then certainly it's true that a sub 3 would be b plus 2d, and that's 17. The 19th term would be b plus 18d, and that equals 65. and what we have here are two equations with two unknowns. And in fact, it's very easy to solve. We're just going to subtract the first equation from the second equation. Subtract, we get 16d equals 48. Divide by 16, we get d equals 3. And then plugging into A3, we get that the initial term is 11. So now we have the initial term, the common difference. We can set up the general formula. The 10th term will be initial term 11 plus common difference 3 times 10 minus 1, which is 9. 3 times 9 is 27. We add that, we get 38. And 38 is the 10th number on the list. An arithmetic sequence is one in which the terms have a common difference. Any evenly spaced list is an arithmetic sequence. Other examples include consecutive multiples of a number, consecutive odds or evens, and numbers which, when divided by the same divisor, have the same remainder. The nth term of any arithmetic sequence is given by the formula a sub n equals a sub 1 plus d times n minus 1. In the previous two videos, we talked about sequences that have an algebraic definition for each term, a sub n. If we have a clear formula for a sub n in terms of the index variable n, then we can calculate the value of any term we want. That is one way to define a sequence. And so that includes both the algebraic sequences as well as arithmetic sequences for which we can construct a formula. This video is about a whole other category of sequences defined in a very different way. To discuss this category, I will begin with a famous sequence from the history of mathematics, the Fibonacci sequence. This is the Fibonacci sequence. What is the pattern here? It's not clear at all, just glancing at this, that there's a discernible pattern. The first two numbers, which I'm going to call the seed numbers, are both equal to 1. And incidentally, this term seed numbers, this is not a widely used term. Some books use this term, but you will not see this everywhere. But this is the term I'll be using in this video, the starting numbers, the seed numbers. So we have two 1s. Then we get the 2 just from adding those two 1s. We get the 3 by adding the 1 and the 2 before it. Then we get the 5 by adding the 2 and the 3 before it. Then we get the 8 by adding the 3 and the 5 before it. After the first two seed numbers, we get each term by adding the two terms before it. That's the pattern here. First of all, I want to be clear. The test will not expect you to look at a sequence of numbers and recognize a pattern such as this for yourself. That is well beyond anything the test would expect. But the test will expect you to understand the algebraic representations of such sequences, and so we need to talk about that. Let's think about this. A sub n is the nth term on the sequence. It's the nth number on the list. Now, in a recursive sequence, this is going to be defined in terms, say, of the number directly before it on the list. The term directly before it would have an index number that is 1 less, n minus 1. So a sub n minus 1 is the term immediately before the nth term. If a sub n is defined in terms of a sub n minus 1, this is called a recursive definition, and the sequence is a recursive sequence. That is to say, a sequence in which each term is defined in terms of the previous term or in terms of previous terms. In a recursive sequence, the nth term is defined in terms of either the single previous term or, as we'll see in a moment, multiple previous terms. The test would have to give us a formula for a sub n in terms of a sub n minus 1, and it would also have to give us a typical seed value, typically the value of the first term. So the test would give us that, and we need to recognize that it is a recursive sequence, and we need to recognize what to do. So for example, here's a very simple recursive sequence. We have a seed term. Let's just play around with this. We know that the first term is 1. Well, what's the second term? Well, the second term would be 2 times the first term plus 1. That's 2 times 1 plus 1, which is 3. The third term would be 2 times the second term plus 1. Well, that's 2 times 3 plus 1, which is 7. The fourth term is 2 times the third term plus 1. So this would be 2 times 7 plus 1, that's 15. The fifth term would be 2 times the fourth term plus 1. So this should be 2 times 15 plus 1. This is 31. Notice that for a recursive sequence, there's no way to jump right away to the value, say, of a sub 5, the fifth number on the list. We have to work our way term by term from the starting seed up to the value we want. So this is very different from the algebraically defined sequences or arithmetic sequences. We can't just jump to a later term. We have to ratchet our way up term by term, finding every term along the way up to the term that's desired. So obviously the test is never going to ask you to find, say, the 40th term. It's going to ask something more like just find the 5th or the 6th term, something where you'd only have to do a few steps of the calculation. Here's a practice question. Pause the video and then we'll talk about this. Okay, we have a recursively defined sequence. We have a seed value. So the first term is clearly 1. The second term is the first term minus 1 squared plus 3. So 1 minus 1 is 0, plus 3, that just gives us 3. So the second term is 3. Now the third term is going to be that second term minus 1. We're going to square that plus 3. So that's going to be 2 squared, which is 4, plus 3, which is 7. The fourth term now, we're going to take 7, we're going to subtract 1, we're going to square it and add 3, and this gives us 39. And that is the fourth term of this sequence. Those were examples in which each term depends on the term immediately before it. In some sequences, such as the Fibonacci sequence mentioned earlier, these depend on the previous 2 terms. For the hardest recursive sequences on the test, a sub n will be defined in terms of both a sub n minus 1, which is the immediately previous term, and a sub n minus 2, which is the term before the previous term. So these are the 2 preceding terms. Think about the Fibonacci sequence again. This sequence has the 2 seed values. The first value is 1, the second value is 1, and each term is the sum of the 2 previous terms. So algebraically, we would say a sub n equals a sub n minus 1 plus a sub n minus 2. That's the symbolic representation of the rule that creates the Fibonacci sequence. For a sequence that has the same rules as the Fibonacci sequence, but different seed values, different starting values, find the value of a sub 6. So pause the video here and then we'll talk about this. Okay, so we have our seed values 1 and 3. The fourth term, we're going to add those 2, so it's going to be 4. The fourth term, we're going to add the second and third term, 3 plus 4, which is 7. For the fifth term, we're going to add the fourth term and the third term, so that will be 7 plus 4, which is 11. And then to find the sixth term, we'd have to add the fifth term plus the fourth term, so this would be 11 plus 7, which is 18. And that's the sixth term on the list. Here's a practice problem. Pause the video and then we'll talk about this. A sequence is defined by s sub n equals s sub n minus 1, quantity minus 1, times s sub n minus 2 for all n greater than 2, and it has the starting values of s sub 1 equals 2 and s sub 2 equals 3. Find the value of s sub 6. So once again, there's no way to jump right away to the sixth term on the list. We have to find them in order. The third term, the fourth term, the fifth term, up to the sixth term. So these are our starting terms. The third term is going to be the second term minus 1, so 3 minus 1 is 2, times the first term 2. That's 2 times 2, which is 4. The fourth term is going to be the s sub 3, which is 4, so 4 minus 1 is 3, times the second term, which is 3. We get 3 times 3, which is 9. That's interesting. It looks like we're getting squares. We wonder, will that pattern continue? The fifth term is going to be the fourth term minus 1, so 9 minus 1 is 8, times the third term, which is 4. 8 times 4, that's 32. So we don't continue with squares. It looks like they get bigger. Now the sixth term, we're ready for the sixth term. This is going to be the fifth term minus 1, 32 minus 1, which is 31, times 9. And 31 times 9, we can do that without a calculator. 30 times 9 is 270, so 31 times 9 is 279. And that is the sixth term on the list. In recursive sequences, each term, a sub n, is defined in terms of one or two previous terms. It's defined in terms of a sub n minus 1, and maybe in terms of a sub n minus 2. The numerical values for one or two terms will always be specified. With a recursive sequence, there is no way to jump immediately to the value of a term such as the sixth term. Instead, we have to find each and every term from the start up to the desired term. So now we'll talk about inclusive counting. First of all, consider this very easy question. On a warehouse shelf, there are 27 boxes numbered from 1 to 27. John carried the first 8, so he carried boxes 1 through 8, and Mary carried the rest. How many boxes did Mary carry? Well, obviously what we would do is simply subtract. 27 minus 8 is 19. That would be the number of boxes that Mary carried. So that's a really easy question. Now consider this superficially similar question. A workshop's first day was April 8th and its last day was April 27th. How many days did the workshop run? We might be tempted to do the same subtraction, but that will not produce the correct answer. There's a crucial difference between this problem and the previous box carrying problem. Now if we think about it, in the box carrying problem, Mary carried box number 27, but box number 8 was not included among the boxes she carried. Box number 8 was the last box that John carried. Ordinary subtraction works absolutely fine there. So in other words, one of the numbers was not included and one of the numbers was included. In the workshop problem, both April 8th and April 27th, both endpoints are included as part of the workshop. Ordinary subtraction is not equipped for this because the difference that results from ordinary subtraction automatically excludes the lower endpoint. Let's think about this. If we subtract 27 minus 8 equals 19, that gives the whole group of days, and in this group it excludes April 8th, but includes April 9th and all the days up to and including April 27th. So we have the whole workshop except for the first day. So all we have to do really is just add one more for this excluded day at the beginning. So the workshop was 27 minus 8, which is 19, plus 1, which is 20. It was 20 days long. This way of counting is known as inclusive counting. We always use inclusive counting when both endpoints, the starting value and the ending value, are included in what we are counting. We perform the ordinary subtraction for this situation, then we add 1 to the difference to account for the included starting value. So think about this question for a minute. You can pause the video if you need to, and then we'll talk about it. Okay. Contract negotiations opened on the morning of March 20th, continued every day without break, and ended late in the evening of May 10th. For how many calendar days were the contract negotiations in session? Well, let's see. First of all, in March, we're talking about the 27th to the 31st. That's the end of March. So how many days there? That would be 31 minus 20 plus 1 for the inclusive counting, that's 12 days. So 12 days in March, the whole month of April, so that's 30 days, and then the first 10 days in May. So altogether, that's 12 plus 30 plus 10, 52 days. So that's how many days the contract negotiations were in session. Here's another one. Pause the video and then we'll talk about this. Okay, how many multiples of 8 are there from 200 to 640 inclusive? Well, 8 goes into 225 times, 8 goes into 640 80 times, so it's really like counting the integers from 25 to 80. And both of those are included, so we're just going to do 80 minus 25 plus 1 is 56. And that's how many multiples of 8 there are, starting at 200 and going all the way up to 640. We use inclusive counting whenever the situation demands that both endpoints, the lowest value and the highest value, are part of what we are counting. We perform the ordinary subtraction of high minus low, then add 1 for the included lower endpoint. Now we can talk about sums of sequences. Sometimes the test will ask us for the sum of a long sequence. For example, what is the sum of all the multiples of 20 from 160 to 840? We'll actually talk about the answer to that question later in this video. Before we talk about that, a famous legend from the history of mathematics will help us figure out this sort of question. The great mathematician Carl Friedrich Gauss was known as the Prince of Mathematics, and he was precocious as a child. According to the story, the 5-year-old Gauss was pestering his kindergarten teacher with too many questions, and she wanted to keep him busy for a while, wanted to kind of shut him up with some kind of hard kind of question. She asked him to add all the integers from 1 to 100, and to her astonishment, Gauss produced the answer in seconds. How did he do that? Well, the 5-year-old Gauss noticed the following. Suppose we have all the numbers from 1 to 100 added up. Take off the first and the last. 1 plus 100, that's 101. Now take off the next pair remaining from the beginning and the end. 9 and 2 and 99, they also add up to 101. Then the next pair, 3 and 98, they also add up to 101. So you see a pattern here. We could keep on taking pairs from the outside. They would all add up to 101. And of course there are 100 numbers, so that would be 50 pairs. Clearly we could pair all the numbers up. We'd wind up with 50 pairs, each of which has a sum of 101. This means that the total sum has to be 50 times 101, which is 5,050. And that's exactly what the 5-year-old Gauss figured out. Let's generalize that to the sum of the first n positive integers. So the first pairing would be n plus 1. The second pair would be n minus 1 plus 2, which is also n plus 1. Then n minus 2 plus 3, which is also n plus 1. So each pair would be n plus 1. That would be its sum. And there'd be n over 2 pairs, so the sum of the entire sequence has to be n times n plus 1 over 2. That is the sum of the first n positive integers. That's a good formula to know. And again, don't memorize this. As we say often in these videos, don't simply memorize this formula, but if you understand how we got to this formula and how we put it together, that is real mathematical understanding. Even more generally, suppose we have any evenly spaced list that has n items with a lowest term of a sub 1 and a final term of a sub n. If we pair from the outside, each pair will add up to a sub 1 plus a sub n, the sum in the first and the last terms. If there are n total terms, there will be n divided by 2 pairs of terms, and each pair will have the same sum. So the sum of the list, we could write it this way, or we could write it this way. Either one of these ways is fine. This is an enormously important formula, and once again, don't simply memorize. Please understand how we built this formula step by step. Now we can go back to the practice question we had at the beginning. Pause the video and see if you can figure this out for yourself, and then we'll talk about it. Okay, we have to determine how many terms there are. So 160, that's 8 times 20. 840 is 42 times 20. So we're going from the 8th multiple to the 42nd multiple. And so how many terms? We have to use inclusive counting here. So inclusive counting, 82 minus 8 plus 1 is 35. So that's the number of terms. So the number of pairs is half of 35, which is 17.5. And the sum of the list, the beautiful thing is that when we add 160 and 840, we get 1,000. And so it's just 1,000 times 17.5, or 17,500. What is the sum of all the multiples of 5 that are greater than 100 and less than 200? Pause the video, and then we'll talk about this. This is a tricky problem because we're not including 100, we're not including 200, but we are including all the multiples between them. So 100, of course, is 5 times 20. That's not included. But if we add 5 more, 105, that should be 5 times 21. So that is included. And that's, in fact, the first term. Now go to the end of the list. 200 is 5 times 40. That's not included. But if we subtract 5, go down to 195, that should be 5 times 39. And that's a sub n. So we have a sub 1 and a sub n. Now we just need to know the number of terms. How many terms are there from the first term, which is 5 times 21, to the last term, which is 5 times 39? Well, it's the same as how many numbers are there from 21 to 39. And we get that from inclusive counting. 39 minus 21 plus 1, 18 plus 1, or 19. Now we have all the pieces for our formula. N equals 19, a sub 1 equals 105, a sub n equals 195. So we're going to plug this into the formula. I'm going to do the following. First of all, I'm going to add the first and the last term and get 300. That's a nice round number. I'm actually going to factor out the 3 and multiply it by the 19, so we get 57 times 100 divided by 2. Now I'm going to do 57 divided by 2, which is 28.5, because of course 56 divided by 2 is 28, 58 divided by 2 is 29, 57 divided by 2 is right between them, 28.5. And then multiply 28.5 times 100, we get 2,850. So we go back to the answer choices, and we choose answer choice D. To add sequences of evenly spaced numbers, pair the numbers by the first and last to produce pairs of a constant sum, then multiply by the number of pairs. Once again, I would urge you not merely to memorize the formulas given here. Instead, understand the logic of the procedures explained. Now we'll talk about a particular kind of problem that combines integer properties thinking with algebraic thinking, about consecutive integers. So the word consecutive means in a row or one following the other. So the term consecutive integers could mean any number of integers in a row. Could be the numbers from 1 to 100 or just 1, 2, 3. Those are consecutive integers. In fact, a set of 3 or more consecutive integers could contain both positive and negative numbers if the set contains 0. So for example, the set of 3 numbers, -1, 0, 1, those are 3 consecutive integers, and one is positive, one is negative, and one is neither positive nor negative. Some basic facts. A set of n consecutive integers will always contain one number divisible by n. Now, why is that? Well, if you think about it, say the multiples of 17. Well, every 17 numbers, you get to another multiple of 17. The multiples of 17 have to be spaced 17 apart. And so if you think of the numbers as kind of wallpaper, every 17 spaces you go ahead, you're going to come to another multiple of 17. So if I just take a random swath of 17 numbers, somewhere in there, there's going to have to be a multiple of 17. So for example, here, I have 7 numbers, and so it's guaranteed that there's going to be one number divisible by 7 in this group. That is guaranteed, and that one is 21. If I go larger, it's not necessarily guaranteed. As it happens, there is a multiple of 8 here. There's not a multiple of 9 here. If we go lower than 7, we're guaranteed that we will have at least one. So if we go down to 6, we have one multiple of 6, 24. We got lucky. We actually got 2 multiples of 5. We didn't have to get 2 multiples of 5, but we got 2 multiples of 5, 20 and 25. And then as you go down smaller and smaller, you'll get more and more multiples. If n is odd, then the sum of a set of consecutive integers will always be divisible by the set. So let's take these same 7 integers. We add them up. They add up to 161, and 161 is divisible by 3. And in fact, notice that when we divide it by 3, we get the median of the set. The mean and median of the set is the middle of the set. And if there's an odd number in the set, the median will be a number in the set. This is something we'll talk about a little more when we get to statistics. In a set of 3 consecutive integers, you could have 2 evens and 1 odd, or 2 odds and 1 evens, depending on whether you start. In a set of 4 consecutive integers, you must have 2 evens and 2 odds. So in a set of 3, we start at 20, we have 2 evens and 1 odd, but if we start at 21, we get 2 odds and 1 even. Sets of 4, notice that we have to get 2 evens, 2 odds, and notice because it's a set of 4, at least one of them has to be divisible by 4. So in the first set, 20 is divisible by 4. In the second set, 24 is divisible by 4. Because it's a set of 4, at least one number has to be divisible by 4. Now here's where it really gets interesting, the algebraic representations of consecutive integers. It's relatively easy to recognize consecutive integers when you're given actual numbers. The test likes to give algebraic representations of consecutive integers. So what does this look like? Well, for example, all of these are sets. So n plus 1, n plus 2, n plus 3, that's a little more obvious that we're getting the numbers one after another. It can also be with subtraction or subtraction and addition, n minus 2, n minus 1, then n plus 1, then n plus 2, that's fine. N plus 15, n plus 16, n plus 17, it would be odd if that were the case, but notice those are still spaced one apart. And so as long as n is an integer, then all of these will be sets of consecutive integers. Here's a practice problem. Pause the video and then we'll talk about this. Okay. We're told that n is an integer greater than 50. So in other words, it's not going to be convenient or easy to plug in numbers for this. So we have to be a little more clever. Well, notice that this expression is an expression that can be factored. And so we can factor out the n and then rearrange the terms. Notice that n plus 1 is 1 more than n. N minus 1 is 1 less than n. N minus 2 was 1 less than that. So what we have here is 4 consecutive integers, a product of 4 consecutive integers. Well, what do we know about 4 consecutive integers? We know that 2 of the numbers are even, 2 of the numbers are odd, so there must be a multiple of 4 and then another even number. Well, if we multiply a multiple of 4 by an even number, we're going to get something divisible by 8. So it's definitely divisible by 8. We have a multiple of 4. We also have a multiple of 3. Well, anything divisible by 4 and divisible by 3 is going to be divisible by 12. But 18 we don't really know. You see, 18 is 2 times 3 times 3. Are we going to have 2 multiples of 3 in this set? Well, maybe or maybe not. You know, if we had 11, 12, 13, 14, that would just have one multiple of 3, 12. But if we had 12, 13, 14, 15, then we have 2. We could, by chance, have 2 multiples of 3, but we don't necessarily have to have 2 multiples of 3. And so we can't guarantee, because this is a must be true, we can't guarantee that it's divisible by 18. So we'll eliminate that, and the only ones that work are 1 and 2. Sometimes the test may also ask about consecutive multiples of a number. For example, 25, 30, 35, 40 are consecutive multiples of 5. 35, 42, 49 are consecutive multiples of 7. 48, 51, 54 are consecutive multiples of 3. 65, 78, 91, and 104 are consecutive multiples of 13. So you're not necessarily asked to recognize multiples from sets of numbers that are given, but you'll be asked about a set of consecutive multiples. So here's an example question. Pause the video and then we'll talk about this. So 135 is the lowest number in a set of 41 consecutive multiples of 5. What is the difference between the lowest and highest numbers in the set? So this is kind of a sequence in a way. We know the first number in the set is 135. The second number is the next multiple of 5, so it must be 135 plus 5. I'm just going to write it like that. The next number is going to be 135 plus 5 plus 5, or 135 plus 5 times 2. And then 135 plus 5 times 3. So we see a pattern developing here. So the nth term is going to be 135 plus 5 times n minus 1. Notice that the factor by which we're multiplying here is always 1 less than the number of the term. And so that's why the nth term is 135 times n minus times 5 minus 1. 5 times n minus 1. So the 41st term is going to be 135 plus 5 times 40. I'm just going to leave it like that. Well, the first term is 135. The 41st term is 135 plus 5 times 40, and we want the difference. What's the difference between the highest and the lowest? So we subtract and cancel out the 135, and the difference is just that product, 5 times 40. Well, 5 times 4 is 20. 5 times 40 is 200. And so we choose answer choice B. In summary, we talked about consecutive integers, some of the examples and the basic rules, and those are very handy number facts to keep in mind about consecutive integers. We talked about the algebraic representation of consecutive integers, recognizing the pattern, and then applying the basic rules from consecutive integers. And finally, we talked about consecutive multiples of a number.
Word problem strategies. So far, throughout the word problem module, we have talked about the very straightforward algebraic solutions to problems. And always those work. That's always one way to solve the problem, but it's not the only way. And in this set of videos at the end, we're going to be talking about some alternative strategies that you can use. The first strategy we're going to talk about is backsolving. If all 5 answer choices are numerical, if we get 5 numbers, then we can use the strategy known as backsolving. Backsolving means that we start by assuming one of the numerical answers is the answer to the question. We pick one and we say, okay, let's pretend that this is the answer. From this we work backwards and see if it actually makes sense. If the answer doesn't work, we often can tell that we needed a larger or smaller number for the end result, and this allows us to eliminate more than one answer at a time. A relatively simple way to approach this is always begin with answer choice C. So this is the most straightforward backsolving strategy.
If you start with C, that will be correct 20% of the time, and if it's not correct, you will be able to eliminate either the two larger answers or the two smaller answers. So just in one trial, even if you don't get the right answer, you can usually eliminate 3 answers at once. And then all you have to do is test one of the remaining 2. There's an alternative strategy. So this is a little more sophisticated, but you can certainly use this if you like. Alternate strategy would be to pick B first. There's a 20% chance that it's the official answer and another 20% chance that it's too big, which would make A the official answer. That gives you a 40% chance of being right on the first guess. And of course, if B doesn't work, then you'd use D next, and then that would narrow everything down to a single answer. So that's a slightly more sophisticated approach, but statistically, it gets you to the right answer on average a little bit faster. So certainly it's something to consider. Okay, here's a practice question. Pause the video, and then we'll talk about this. Okay, this is a relatively easy practice question. In a certain state, schools pay 2% tax on food and 8% tax on stationery. The school placed a combined order of $500 on food and stationery and paid $19 in tax on the order. How much of that money was spent on food? So we could solve this. We could set up algebra and solve this. Instead of doing that, we're going to explore a backsolving approach. So we're just going to pick C. We're just going to say, pretend 300 is the answer. That means they spent 300 on food, so they must have spent 200 on stationery. There's a 2% tax on food, so 2% of 300 gives us $6. There's an 8% tax on stationery, so that gives us $16. The total tax there is $22, and that's too much. They paid $19 in tax, so 22 is too much. And so what this means is, to pay less in taxes, the school must have spent more on food and less on stationery, because food is taxed at a much lower rate. So if they spent more on food, they would be paying less in taxes. So right away, we can eliminate A, B, and C. So this is great. Even if we were running out of time, we could guess from the remaining 2, and we'd have a very high likelihood of guessing by chance the right answer, because 3 answers have already been eliminated. But that was pretty quick, so we probably would have time still to do another round of back solving. So another round, we could pick either D or E. I'm just going to pick E because it's divisible by 100. It's just slightly more convenient, so that's the only reason I'm going to pick it. Let's say E is the answer. Well, that means that food costs $400, so stationery costs $100. The food tax, 2% of $400 is $8. 8% of 100, of course, is $8, and that would give us a total of $16 in tax, which is too little. So A, B, and C are too big. E is too little as far as the amount of tax, and so that leaves the only right answer. The only possible answer would be D. So after 2 choices, we are done. We know that D has to be the answer. Here's another practice question. Pause the video, and then we'll talk about this. Okay, this is a mixture problem. If you haven't seen the video on mixture questions, it may help to go back and watch that video before talking about this particular problem, because this particular problem depends on knowledge of that video. A chemical supply company has 60 liters of 40% of some chemical. That chemical happens to be nitric acid. You don't need to worry about that. How many liters of pure undiluted acid must the chemists add so that the resultant solution is a 50% solution? So we're going to add solute to increase the concentration, and we want to increase it to 50%. So C is a nice round number, so we'll just pick C as our answer. Before we even pick it, notice that the amount of solute in the beginning solution, 40% of 60, is 24 liters. There are 24 liters of the acid in the initial solution. So now let's pick C. We add 20 more liters of acid. And so that means that we have a total concentration of 44 liters. That is the amount of acid in the solution. And of course, the total solution, the volume of the solution, is going to be 80 liters. And so we want to know, do we have the right concentration? Well, we don't have to do the division. We can see that 44 is more than half of 80. So we don't even need to know the exact number. All we need to know is the concentration would be over 50%. So this is too high. We've added too much acid. So right away, we can eliminate C, D, and E. All of those add too much acid. So now we have to pick either A or B. It doesn't matter. I'll just pick A. Suppose we add 12 liters of acid. Well, now the total concentrate is 24 plus 12, 36 liters of acid. So that's how many liters of acid total would be in the solution. And at that point, the total volume of the solution would be 72. And notice that 36 is exactly half of 72, so this would be a 50% solution. This answer actually works, so we picked the right answer here. The answer is A. In summary, when all 5 answer choices are numbers, one alternative strategy is to solve by backsolving. So the very straightforward approach is start with answer C, try this as the answer to the problem to see if it works in the scenario. If C doesn't work, the information about too big or too small will allow us to eliminate other answers. And remember, an alternate strategy would be to pick, for example, B, and then you might be able to determine that either B or A is the answer, depending on whether it was just right or too big or too small. And if it didn't work, then you could pick D, and that second choice would allow you to narrow everything down.
Picking numbers is an incredibly useful strategy, especially if you're the kind of person who does not actively enjoy doing algebra. Though I don't know if there are that many people who actively enjoy doing algebra. All right, so this strategy is particularly applicable when you're dealing with questions that have variables in the question stem and variables in the answers. For instance, a question like this. So take a look at it. I know it looks scary now, but by the end of this lesson, you will have a methodical way to attack a problem like this. So just to point out, right, we have a bunch of variables in the question. We got X, we got Y, we got Z, and then in these answer options here, we have a bunch of X's and Y's and Z's. So before we do a problem like this, let's start out with an easier version of it. A machine produces J widgets every K days. How many widgets will the machine produce after M weeks? And then again, I have my answer options, which have variables in them. And we're going to walk through this step by step. So step 1 is pick your own smart numbers. What do I mean by smart numbers? Well, we'll talk about that in a little bit. Some numbers are better to pick than others, but for now, we'll just say pick any number you want. Let's say that J equals 10, K equals 2, and M equals 3. So from now on in the problem, these are concrete. The machine produces 10 widgets every 2 days. So how many widgets will the machine produce in 3 weeks? Step 2 is to solve the problem so that you get a target answer. Well, I'm just going to solve this problem as if these numbers were in it. So the machine produces 10 widgets every 2 days. I might do some mental math and say, okay, well, that's 5 widgets per day. Per 1 day. So how many widgets will it produce in 3 weeks? Well, in 1 week there are 7 days. In 3 weeks there are 21 days. So I'm going to multiply 5 by 21. 21 times 5 gives me 105. So 105 is my target answer. And that's important. And now that I have my target answer of 105, step 3 is to plug the chosen numbers, that's the numbers I chose right up here, plug those into the answer options and see which one spits out the correct answer. So now I want to plug these random numbers that I just chose into the answer options, and whichever answer option gives me my target answer of 105 is the correct one. Okay, so let's get to work. J times K times M. 10 times 2 times 3. Got 10 times 2 times 3. That looks like 20 times 3, which is 60. Nope, that's not 105. Okay, 7 times K looks like 14. divided by j times m, 10 times 3, 30. Well, I don't even really need to do the math there. I can tell that's not going to be 105. So A and B are both out. How about 7 times j, 70, divided by k times m, 6. Again, feel free to check that in your calculator. It's nowhere near 105. And then we got k, which is 2 divided by 7 times j times m. Now that's a big number. 7 times 10 times 3. 2 over a huge number is not 105. And then I'm left with this one. 7 times j times m over k. So I got 7 times 10 times 3 over 2. What does that equal? 70 times 3 is 210. Again, feel free to check this on your calculator. Divided by 2 is 105. Well, would you look at that? Answer option E magically produced the target answer. And I know what you're thinking. You're probably thinking, like, well, why does this work? How does this work? How is it allowed? The idea behind it is that because the problem is giving you generic values, that is variables, right? If I say X apples, I'm not specifying how many apples I have. It should work with any numbers that you choose. So you can just choose your own numbers, as long as, and this is important, as it conforms to listed restrictions. And we're going to see this in a little bit, but if the problem says that, X has to be greater than 2, then you got to pick a number for X that's greater than 2. But before we get too excited, let's talk about a caveat here. So we'll go back to this question, right? The widgets, the days, the machine, the weeks. But instead of picking numbers like 10, 2, and 3, let's say that I had picked, 1, 1, and 1. I'm just not feeling particularly creative, and I just choose 1. Well, if I plug these numbers in, watch what happens. So I plug it in for B, then 7 times 1 divided by 1 is 7. If I plug it in for C, then it's 7 times 1 divided by 1, also 7. And then if I plug it in for the variables in E, then it's 7 times 1 times 1 divided by 1, 7. So I have 3 correct answers, and I don't know which one is the correct answer. To avoid this situation, you want to pick smart numbers. Now, I referenced this before. Let's talk about that. What are smart numbers? Well, for one thing, not 0 or 1. As we just saw, right? When you plug in 1 to a bunch of variables, it doesn't change anything. It all stays the same. And when you plug in 0, everything goes to 0. So 0 or 1 are absolutely numbers you do not want to pick for this. Along with that, you generally don't want to pick numbers that already appear in the answers. And the reason for that is if I have an answer option, for instance, like 7 over x, and I pick 7 for x, well, then this is just going to become 1. And then we have the same problem as we do up here. Finally, and this is pretty optional, but if you want to try it, I would recommend it. Keep your numbers realistic to the context of the problem. So that means that if you're talking about someone's salary, maybe don't have them earn $2 a year. The reason for this is it acts as kind of a last check for you. If you pick realistic numbers, then you should expect your answers to be realistic. So if you come up with unrealistic answers, then it kind of alerts you that you've done something wrong. And then finally, even if you follow these guidelines, you pick smart numbers, and you still end up with duplicate answers, it happens sometimes. You just want to tweak your numbers a little bit, right? It's very, very rare, but it does happen. Let's try that difficult problem we saw at the very beginning of the lesson. So go ahead and put your video on pause right now, give this a shot on your own, and then we'll talk about it together. All right, here goes. A salesperson earns a 2.5% commission on the first X dollars of sales, a 5% commission on the following Y dollars of sales, and a 7% commission on all sales thereafter. If the salesperson made a total of Z dollars in sales, where Z is greater than X plus Y, how much did the salesperson earn in commissions in terms of X, Y, and Z? So first things first is recognizing that this is exactly the kind of problem where we can plug in our own numbers. Why? Well, again, because I have variables in the question and I have variables in the answer option. So that's the green light for me to plug in my own numbers. But I need to be careful, because this problem, unlike the last one, has a restriction. It tells me that whatever I pick for z must be greater than x plus y, whatever I pick for x plus whatever I pick for y. So as long as I abide by that condition, I'm good to go. And I don't know what numbers you picked, but I went ahead and chose these numbers. X is 1,000, so he earns a 2.5% commission on the first $1,000 of sales. There it is. A 5% commission on the following $5,000 of sales. We'll write that in. And a 7% commission on all sales thereafter. If the salesperson made a total of $10,000 in sales, how much in commissions did the salesperson earn? Now, the key to solving this kind of problem is not to get hung up on all of the algebra in it, right? The more you worry about all the x's and y's floating around, the less you pay attention to the real simplicity of this problem. So let's actually plug these numbers in and solve it for our target answer. Here it goes. So I'm going to earn a 2.5% commission on the first $1,000 of sales. How do I calculate that? Well, it's 0.025 times 1,000. And then I'm going to earn a $5,000 commission on the next $5,000 of sales. Now here's the tricky part. I'm going to earn a $7,000 commission on all sales thereafter. That doesn't mean I earn a $7,000 commission on 10,000. 10,000 was the total number of sales that I made. How many sales did I make after I sold 1,000 and 5,000, so 6,000? Well, to get to 10,000, I sold 4,000, right? I sold 1,000, I sold another 5,000 for a total of 6,000, and then I need to make 10,000, so that's another 4,000. So it's going to be 7% of 4,000. If you mess that up, that will do you in. Okay, so what are these actual numbers? 25% of 1,000, or excuse me, 2.5% of 1,000 is $25. 5% of 5,000 is $250, and 7% of 4,000 is $280. And if I add these all together, I get $555. And that is my target answer. And now that I have my target answer, what do I need to do? Well, I need to plug the numbers that I chose into the answer options and see which one gives me my target answer. Now, A is a very, very tempting answer option, especially if you don't use this picking number trick. I mean, look, it matches the commission structure pretty closely. I got 2.5%, I got 5%, and I got 7%. But the problem is, this is 7% of the whole amount of sales, right? And we're going to see why this doesn't work when we plug in the numbers. Let's plug in 1,000. So 1,000 times 2.5%, we saw already, was 25. We plug in 5,000, 5% of that is 250. And then we plug in 10,000, we get 700. This, 700 plus 250 plus 25, does not equal our target answer, and so it's not correct. The correct answer is actually B. And we plug in our numbers, we see that, right? I got 7% of 10,000, so that's 700, right? Minus 20% of 5,000, that's 100. Minus 4.5% of 1,000, 45. Sure enough, 700 minus 100 minus 45 equals 555. Now, you could have solved this problem algebraically, and I encourage you to do that. But if you had, it would take a while, and you'd still end up at B. So, when you see variables in the question and variables in the answer, and you don't want to do the algebra, you can use this method.